In this lesson, we'll talk about continuity, which is a property that a given function will have, and we'll look at a formal and an informal definition. So actually, let's look at the informal definition first. A function is continuous if you can draw its graph without lifting your pen or pencil from your paper. So for example, you could draw an equation that looks something like this. So it's continuous, I'm drawing it without lifting my pen from my page. And so the idea is there's no breaks or asymptotes or holes in the graph, and it's one smooth curve in this case. We'd say that this function that I drew is continuous. Now I'm going to adjust it a little bit, so maybe I'll erase this part over here, and I'll throw in a spot where it is not continuous. So for example, you could put an open circle here, redefine the function up here, and then draw this as your graph. This graph is now continuous everywhere except for at this x value, whatever it happens to be. I'm going to mark 2 places on this graph. I'll choose an x value here, I'll call it a, and then here at this x value b, the function is not continuous. So I'll note that at x is equal to a, f is continuous. But at x is equal to b, f is not continuous. Now let's compare this to this formal definition up here. Why is this function continuous at a, at this spot? The reason is the value of the function, which is f of a, and the limit as you approach it are the same. It's saying all the y values are heading to the value of the function at this spot. And that's precisely what this definition says. So formally, a function is continuous at a if the limit exists, the value of the function exists, and the 2 things are equal to each other. So this spot is approaching this spot. I'd like to list those things out here, what this definition actually says. It says 3 things. It says the limit as x approaches a of the function exists. So that is the limit from the left is equal to the limit from the right. Second, it says that f of a is defined. There's actually a value of the function there. And here, there is. We call that f of a. And 3, not only is the limit existing and the function defined, but finally, the 2 things are in fact equal to each other. If any one of these 3 things does not happen at some spot, we would say that the function is discontinuous or just simply not continuous. Let's check this out in an example. In example 2, we have a function f, and it's a piecewise defined function. I'd like to determine where it is discontinuous and explain why using the formal definition of continuity. So first of all, I'm noticing that a change is occurring at x is equal to 1. If you see a piecewise defined function and you're looking for discontinuities, a value over here is a good spot to look at. That being said, let's sketch this thing. If we're less than 1, the function is equal to 2 minus x. That is a line that goes through 2 with a slope of -1, and so your equation should look something like this right up until you get to 1, and I'll put an open circle there. So here is a sketch of just 2 minus x when we are to the left of 1. Now at 1, we're defining the function to be 4, so I'll put a closed circle up here. And then finally, if x is greater than 1, the function is actually just equal to x. So that's a line with slope 1 going through the origin, but it starts here. Again, we'll have an open circle because there's no equal sign, and it will increase like this. And here we go. This is the function f. Now, where is it discontinuous? Well, it's definitely continuous if we're to the left of 1 and to the right of 1, but there is clearly an issue happening at x is equal to 1. So I'm going to note that at x is equal to 1, f is discontinuous. And this is the only spot at which that happens. Now the question is, why? looking at the formal definition of continuity, if the function were continuous at 1, it would mean the limit as x approaches 1 of the function is equal to the value of the function at 1. This is what should happen for continuity, but something should go wrong in this definition. So the answer is like, no, something's got to be wrong here. So something goes wrong here, and there's only 3 things it could be. It's either that the limit doesn't exist, it's maybe that the function is not defined, or they're both defined and exist and aren't equal to each other. Well, let's start with the limit as x approaches 1 of this function. Does this exist? So the limit, does this exist? And the answer is yes. If you look at the limit as x approaches 1 from the left of this function, on the left of 1, this function is defined as 2 minus x. And you can simply put 1 in place of x to get 2 minus 1, which is 1. And if you look at the limit as x approaches 1 from the right of this function, on the right of 1, this limit is defined as x. And by direct substitution, it's also 1. These are equal. And that means the limit exists. In fact, the limit as x approaches 1 is this common limit. Okay, so that's not a problem. The limit exists. Is f of 1 defined? So that's like the next question. Is f of 1 even defined? And that's a very easy answer. The answer to that is also yes. And that's because f of 1, by definition, is 4. You put 1 to the function, you get the number 4 back. There is a value there. The issue must be that these 2 things aren't equal to each other, and clearly that is the case. It is, in this example, that the limit as x approaches 1 of the function is not equal to the value of the function at 1. Those are different. The limit is 1, and 1 is not equal to 4. That's what goes wrong in this definition, and that's why formally it is not continuous at x is equal to 1. Let's try this again with a different piecewise function, but something kind of similar. We'll try to find where it's discontinuous and use the definition of continuity to explain why, the formal definition. Okay, to graph this function, we're at 2. If we're to the left of 2, the function is 2x plus 1. That is a function that goes through 1, and it has slope 2, and therefore there'd be an open circle here at 2, and your graph looks like this to the left. Now, if we are equal to 2 and to the right of 2, the function is actually just a horizontal line, which is 3. So at 2, it's defined and is equal to 3, and then it's horizontal like this to the right. And here's a graph of the function f. I was already thinking before this problem started that because it's a piecewise function, the number 2 could be a place where it's discontinuous. And I can see that clearly just by looking at a picture of the graph. It is clear that at x is equal to 2, f is discontinuous. But the real question is why? What goes wrong in the limit definition? So what goes wrong with the limit as x approaches 2 of the function being equal to f of 2? What problems occur? And it could be one of 3 things. Maybe the limit doesn't exist. Maybe the function's not defined. Or maybe they're not equal to each other. So let's see. Okay, first, is f of 2 defined? Start there. And the answer is yes. In fact, f of 2 by definition is 3. So at 2, it's 3, and it exists. What about the limit as x approaches 2 of this function? Does this exist? And here the answer is no. And since the answer is no, it means this can't be true. But let's see. If we look at the limit as x approaches 2 from the left of this function, if you're to the left of 2, you're using 2x plus 1. So this is the limit as x approaches 2 from the left of 2x plus 1. And by direct substitution, that's 2 times 2 plus 1, which is 5. And if you look at the limit as x approaches 2 from the right of this function, well, on the right side of 2, the function is always defined as 3. So this is the limit as x approaches 2 from the right of just 3, and that limit is 3. In fact, you can't substitute 2 anywhere. The issue is these two things are not equal. They're not equal. And because they're not equal, it means this limit does not exist. And if this limit does not exist, there's no way this statement can be true. We call this type of continuity a jump discontinuity. And that's because you can actually see a jump in the graph. It's not just one point that it was removed. It's actually a whole piece of the graph has been shifted somewhere else. I will make one other note about this problem. I'll write that down here. Even though this function is not continuous at 2, you can get a little bit more specific and say, well, if you only consider one side, it is continuous from the right. And that is the limit as x approaches 2 from the right of this function equal to f of the function at 2? And we've done all the work to demonstrate that this is true. If you only consider the right side, the limit we saw was equal to 3, and the value of the function at 2 is also 3. So in fact, this thing is continuous from the right, essentially because we showed that 3, the limit, is equal to the value of the function at 2, which is also 3. You could ask the same thing about continuous from the left. Is this thing continuous from the left? And the answer is no. The limit on the left is 5. The value of the function at 2 is 3, and those two things are different. So I'll say this is not continuous from the left. So not continuous from the left. And the reason for that is, if you look at the limit as x approaches 2 from the left of f, it's equal to 5. And 5 is not equal to 3, which is the value of the function at 2. So you can actually get more specific about continuity. You can consider just either the left or the right side. Here, it was not continuous on the left, but it was continuous on the right. So we've only considered really piecewise functions in our examples about continuity. I want to state a fact, though, about every other type of function that we're going to work with this semester. It turns out that if you have a function and it's one of these, it is continuous on its entire domain. And we'll just assume that as a fact from here forward. So like, for example, polynomials. Where are they continuous? An example of a polynomial is something like y is equal to 5x to the fourth minus 3x squared plus 7. Sums and differences of x's two powers that are positive integers with coefficients. This thing is continuous everywhere on the entire real line. Nothing can go wrong in this function. There are no breaks in the graph, so we can just assume continuity on the entire thing. The same is true for rational functions. An example of a rational function would be something like 2x plus 1 divided by x minus 3. On the domain of this function, it is always continuous. Now, what's the only thing that could go wrong with a fraction? And that would be division by 0. So where is this function not continuous? It's at the number that makes the denominator 0, which is 3. So this thing it's continuous everywhere, except when x is 3. That's the only issue on this function because the function, it's not even defined there. So trig and inverse trig functions, also those are continuous on their domains. For example, Sine of x is continuous on its entire domain. And things like inverse trig functions like tangent inverse or arctangent. On their entire domains, they are continuous, which is from negative to positive infinity. Same goes for root functions. So something like, let's say the square root of x. Where is this thing continuous? For all numbers equal to 0 or greater than 0. The only issue is if you put a negative number under the square root, that would not be allowed. So where it is defined, though, it's continuous. Last two functions to consider are exponential functions. So things like y is equal to e to the x, or maybe y is equal to 3 to the x. Those are also continuous for every single number you could plug in place of x. And lastly, log functions like the natural log of x. Wherever it's defined, it's continuous. And the place where this function is defined is for all positive numbers. So you should have some familiarity with these equations. You could also look at their graphs by plugging them into a graphing calculator. But the big takeaway is, for all of these functions, they're always continuous, except if, for example, you divide by 0, or perhaps put a negative number under a square root. And furthermore, not only are all of these functions continuous on their domains, if you were to add or subtract, multiply or divide, or even compose any of these functions together, like any operation you could think of, it'll be continuous where defined as well. Let's see how this works by looking at our last example. So in example 4, we have 3 functions in parts a, b, and c. All I'd like to do is figure out is where are they continuous. Let's start with part a, f of x, which is equal to sine of x plus 2e to the x plus 4x. This function is continuous everywhere. It is continuous from negative infinity to positive infinity. And why is that? Well, sine is continuous everywhere. 2e to the x is also continuous everywhere, and so is 4x. These are all continuous from negative to positive infinity. Therefore, the sum is continuous from negative to positive infinity as well. There's nothing else to be said about this. There's no computations to do. Each part of this equation is continuous. If you add them together, the whole thing must be continuous too. Let's look at part B. Here we have a function that is rational. It's x plus 7 divided by x squared minus 1. Where is this thing continuous? The only thing that could go wrong in this function is if the denominator was equal to 0, which, if you factor the left, you get x minus 1 times x plus 1. And there's exactly 2 numbers that make this 0, 1 and negative 1. What does this mean? As long as you don't use these 2 numbers, this function is continuous. I'll write it as an interval, but this is continuous on the interval from negative infinity to negative 1, also on the interval from negative 1 to positive 1, and then from 1 to infinity, using parentheses to indicate that we're not using any of those numbers. We're just going right up until you get to it. So on these 3 intervals, this function is continuous. It's another way of saying, as long as you don't put negative 1 or positive 1 into this function, it'll be continuous on its domain. Last one, the natural log of quantity x plus 4. Where is this thing continuous? The only issue that can happen with a logarithm is if you plug 0 into it. You would get an error if you tried to do that in your calculator. Or if you put in any negative number, like negative 7, you get an error message as well. You want to make sure that whatever goes into a logarithm, that it's positive. Said another way, you can take x plus 4, the thing in the logarithm, and check to see where it is always positive. This is a very easy inequality to solve because you can subtract 4 from both sides. This means this function is continuous provided that you put a number bigger than negative 4 in place of x. So this is continuous on the interval from negative 4 to positive infinity. all of these numbers, when put in place of x, will put a positive value into the logarithm.